Firstly, I would like to introduce to you the planar inverted F antenna. What are they? The planar inverted F antenna is a type of patch antenna. That means that it can be mounted on a flat surface. The planar inverted F antenna consists of two main parts, a metal patch and a larger sheet of metal called the ground plane. These patch antennas are usually constructed on a dielectric substrate. The two sheets of metal create a microstrip transmission line. When the length of the microstrip transmission line is shorter than half of the wavelength at the frequency being used, then radiation comes from the edges of the antenna and causes the antenna to act larger than its actual size. What sets the planar inverted F antenna apart from other patch antennas is that it uses shorting pins, which creates its unique shape of an inverted F. Current applications. The planar inverted F antenna has many different types of applications in the real world. Right now, the use of the planar inverted F antenna has increased in the mobile devices market. These devices include things such as laptops, cell phones, and tablets. This increase is due to its low profile and compact size, its omnidirectional radiation pattern, the fact that it's easy to fabricate, it has low manufacturing costs, and has a simple structure. Patch antennas can be directly printed onto a circuit and can be easily modified and customized as well. A real-life example of the usage of the planar inverted F antenna is the Samsung Galaxy S. The network in the US, the CDMA, uses the frequency 850 and 1900 MHz, one to transmit and receive signals, and a receive-only antenna. The Samsung Galaxy S has 6 antennas: the TX-RX cellular antenna, the diversity cellular antenna, the Wi-Fi antenna, the GPS antenna, and 2 WiMAX antennas, one for the TX-RX and one for the diversity antenna. All of these antennas are planar inverted F antennas.
I'm going to be talking about how the planar inverted F antenna works, but before one can understand how a PIFA works, you need to understand how a patch antenna works. A patch antenna is what a PIFA is based off of. So here we have a picture of a patch antenna. There are a few major components to it, mainly the patch in the middle, the microstrip transmission line beside it, and the ground plane. These are all made up of a conducting metal such as copper. The patch and microstrip transmission line sit on top of a dielectric layer. The frequency of the antenna is determined by the length of the patch antenna, while the width of the antenna controls the impedance. The length can be seen here as L and the width is W. So how does a patch antenna radiate? This is a side view of the patch antenna, and as you can see, the length of the patch is lambda over 2, or half a wavelength. You can also see the other components such as the transmission line and the dielectric. The way this works is that the energy flows down from the transmission line. As you can see, the end of the patch is an open circuit, which means that the current at the end will be 0. It will be at its peak in the middle and 0 at the beginning. The voltage will always be 90 degrees out of phase with the current. The electric field can be visualized under the patch as seen here. It is stronger at the end with higher voltage and weaker at the end with lower voltage. At the end, there are also fringing fields, which can be observed, and it is these fringing fields that allow radiation to be possible. The horizontal component of the fringing fields add up in phase and produce the radiation of the patch antenna. The smaller the epsilon r value of the dielectric, the farther the fringing fields travel from the patch. This means that the smaller the epsilon r value, the better the radiation. So what we just saw was called a half-wave patch antenna due to the length. A PIFA is more resemblant to a quarter-wave patch antenna, and that will be discussed now. The major difference is that a shorting pin has now been added to the antenna. This means that the current at the end is no longer 0 as seen in the half-wave patch antenna. This also means that the fringing fields are not on both sides of the patch anymore, but only on the side of the transmission line. The benefit, however, is that the size is reduced by half while still maintaining the same properties as a half-wave patch antenna. Now, if we were to look at a PIFA, you can see it is very resemblant to that of a quarter-wave patch antenna. The length is again lambda over 4, and now a probe feed has been added. This antenna resonates at a quarter wavelength because of the shorting pin at the end. Looking at the diagram, you can see how the PIFA is built. The feed is placed in between the shorting pin and the ground plane. The impedance is controlled by the distance between the feed to the shorting pin. It increases as the distance between the shorting pin and feed pin increases. Using the equation L1 plus L2 minus the width of the shorting pin equals lambda over 4, one can approximate the resonance of the antenna. Overall, a PIFA works in the same way as a quarter wave patch antenna and is extremely useful as it is becoming more and more popular with cellular devices.
So now we're going to talk about the fabrication of the planar inverted F antenna. The first thing to do when you're going to create a planar inverted F antenna is to obtain your design specs. You will need to know how small your antenna has to be, the frequencies at which it will operate, and the materials available to you. When you are constructing your planar inverted F antenna, you will need to have a dielectric substrate sitting between the patch antenna and the ground. Some sample materials that you can use for this dielectric substrate are duroid, FR4, mica, silicon nitrate, alumina, Roger 3210, silicon, and gallium arsenide. Their permittivities are shown here in this table. The material you choose to use will be dependent upon what is available to you, as well as the frequency and bandwidth that you are trying to obtain, which was explained previously in this video. Once you have all of your materials selected, you can begin to create your planar inverted F antenna. Here is a typical design for a planar inverted F antenna. You have your ground plane underneath, your patch antenna over top of that, connected along one edge by a short pin to the ground. Between the antenna and the ground you have your dielectric material, and somewhere along the patch antenna towards the open end you have your feed probe connected. This is generally a coaxial cable. Where this is connected will again depend upon the specifications of your planar inverted F antenna. To connect the short pin to the patch antenna and the ground, you can solder it at both ends. This diagram does not show the dielectric material, but it would simply lie between the dark gray plane, representing the ground, and the light gray plane, representing the patch antenna. Here is the design of another possibility which allows you to reduce the size of your planar inverted F antenna. You can see that all the components remain the same, except now there is an added capacitor between the feed cable and the open end of the patch antenna. Inserting a parallel plate capacitor at the open end compensates for the change in impedance by making your planar inverted F antenna smaller. Again, this can be soldered on. Here's an example of a real-world planar inverted F antenna. You can see that the feed is connected to the edge, and the short pin is on the other side of the antenna, though you cannot see it in this picture. The white black underneath the patch antenna is the dielectric material, and this would be connected to the ground plane. This concludes the discussion about the fabrication of the planar inverted F antenna.
The idea of the planar inverted F antenna comes from a combination of two other pre-existing concepts. The first is a quarter wavelength monopole with an intermediate position feed, which may be used as an active antenna. The second is an inverted L-shape antenna. The L shape allows a reduction in height while maintaining the same current distribution as a straight monopole. Combining these two models, the planar inverted F antenna is obtained. The geometry of a simple single-frequency planar inverted F antenna is as follows. A ground plane. In parallel with the ground plate, there is a PIFA consisting of a simple rectangular patch. A shortening plate is placed at one edge of the PIFA. Finally, a feed point is placed along the same edge. The impedance can be controlled by changing the distance between the short plate and the feed point. An increase in distance will result in an increase of impedance. Another form of the PIFA is a capacitive loading model. Using the capacitive loading model helps reduce the length of the PIFA. Keeping the single frequency model the same, a capacitor is added in between the feed point and the open edge. This is done because when the length of the PIFA is shortened, there becomes a drop in capacitance. To compensate, the capacitor is added in parallel.
Now, let's talk about measuring the performance of PIFAs. First of all, here are some of the important parameters that an antenna has that we might want to measure. Input impedance determines the power loss due to resistance and the phase shift of current and voltage. Gain shows the relative power transmitted in the direction of highest radiation. Bandwidth is the range of frequencies over which the antenna can function, and radiation efficiency is the ratio of radiated power to input power. It is a number between 0 and 1, and it takes into account losses from resistances and dielectric conduction. Finally, the radiation pattern shows the relative power radiated in every direction from the antenna, which, when you visualize as vectors sprouting from the origin, forms a three-dimensional shape. Now, the obvious way to measure an antenna is to build it and then use equipment to conduct tests. One method is to determine the 3D radiation pattern from which other properties can be derived. Because it would be impractical to measure the pattern in 3 dimensions, it is accomplished piece by piece in cross-sections. To accomplish this, the measuring equipment is gradually rotated in one of either theta or phi. Antennas have 3 distinct radiating regions depending on how far you are from the origin. There's the reactive field immediately next to the antenna. Next, there's the near field, and then the far field. Typically, it is the far field that we hear about to show in what manner the antenna will perform. Measuring the radiating far field can be quite difficult because of the distances required before the far field will form. However, in small antennas such as the PIFA, we have small wavelengths. Thus, the far field forms in a relatively short distance, and measurements can be taken indoors in an anechoic chamber. Real-world testing, however, is very costly and time-consuming when you're designing an antenna. It is a lot easier to use a computer to simulate the proposed antenna. A common approach is to use the finite difference time domain method, which discretizes space and time to approximate differentials. The electric and magnetic fields are solved using a leapfrog method, with the electric field being solved within a given volume for one time step, and the magnetic field is solved for the next time step. While the results are not exact, they can approximate reality very closely. To set up a simulation, you need to model the structure of your antenna. This includes both the geometry and the material properties of different parts. The properties can include, for example, the relative permittivity or the conductivity of the material. Next, you define the size and resolution of the simulation box, and set up what happens to the boundaries of the box. Lastly, you define the excitation from which the signal will spawn. In this image, you can see a PIFA I have modeled. The yellow line is the source of this excitation. It is the feed line to the antenna. Now, after running my simulation, much useful data will be produced, such as how the input impedance depends on the frequency, as well as the reflectivity as a function of frequency. This will show the bandwidth that your antenna can operate in, because where the reflectivity is low, your input power is high. Here, we see the radiation pattern of our PIFA at its optimal frequency. It is represented in 2 dimensions in both polar and rectangular plots. Here, theta is the angle from the positive z-axis, and phi is the angle counterclockwise on the xy plane from the positive x-axis. A 3-dimensional model for the radiation pattern can also be generated. Here we see that the electric far field is strongest in the positive z direction, and that there is a dead spot in the negative z direction. In the xy plane, field strength is more or less constant in all directions. So, what can simulations confirm to us about PIFAs in general? One important thing is that the radiation pattern is omnidirectional in the xy plane. Also, by comparing these simulations to those of patch antennas, we can see that for the same operating frequency, PIFAs can be less than half the size. This is a consequence of the shorting pin.
Hello, my topic is how to modify the design of the PIFA to change the bandwidth it uses. First, let's see the PIFA structure. It consists of a planar element, is a capacitor, a feeding point, short circuit plate, and ground plane. The advantage of the PIFA is easy to manufacture, it's cheap and simple structure, but the disadvantage is the bandwidth is limited. Traditional PIFA only has about 8%. And how to modify the bandwidth? There's several ways. The first one is to modify the size of the ground plane. By varying the size of the ground plane, the bandwidth of the PIFA can be adjusted. For example, reducing the ground plane can effectively broaden the bandwidth of the antenna system. To reduce the quality factor of the structure and to increase the bandwidth can be inserted several slits at the ground plane edges. The next method is to modify the feed plates. There are several kinds of the feed plates. Like this is the wire feed PIFA, this is the triangular, this is the bitriangular, this is the rectangular, this is the rounded, and this is the U-shaped strap element. And with different kind of the feed plates, the bandwidth of the PFAR is different. It shows in this chart. And the next method is to put the metamaterials. This can increase the bandwidth. Metamaterials are artificial materials engineered to have properties that may not be found in the nature. Metamaterials usually gain their properties from structure rather than composition, using small inhomogeneities to create effective macroscopic behavior. The next method is to use the thick air substrate. This can increase the bandwidth by lower the Q and increase the bandwidth. The next method is to modify the upper patch. By changing the upper patch to this slope, this shape can increase the bandwidth to about 16%. And there are several ways, like using parasitic resonators with resonant lenses close to main resonant frequency, or adjusting the location and the spacing between two shorting poles, or excitation of multiple modes designed to be close together or far apart depending on requirements, or using stacked elements. It will increase the bandwidth. And that's all. Thank you.